Law of cosine. Solve for A in the triangle below. So I see I'm given an oblique triangle, and I'm given only one angle, a 28-degree angle. I'm given both of the sides adjacent to that angle. So I'm given a 15 unit length and a 20 unit length as the two adjacent sides. So I have one side, the angle in between that side and the next side. This is the side angle side case. Because I'm not given the side that is opposite to the given angle, I cannot use the law of sines. So I'm going to go ahead and develop the law of cosine. So in order to do that, I'm going to drop an altitude from this angle up here. Dropping that altitude creates two right triangles. Let's look at the right triangle on the left with 28 as the given angle and the hypotenuse being 15. For that right triangle, if I'm trying to find the coordinates of the point up here, the point that is the vertex of the angle on top here, if I want to find that point, I'll notice that the x value of that point is just the base of this triangle, one of the legs that forms the right angle, and that the y value is just the height of this triangle. If I can find the length of this leg and the length of this leg of the right triangle, I will have the ordered pair here with the x and y angle. Well, based on that green right triangle, I see that the sine of a 28-degree angle is equal to the opposite y over 15. Sine of 28 is y over 15. And that the cosine of that 28-degree angle is equal to x over 15. And that means that the ordered pair right here, for the vertex of this top angle, that ordered pair is the x value, 15 times the cosine of 28, comma the y value, 15 times the sine of 28. So I'm just solving both of these equations for the x and y value. Once I have that ordered pair, I see that the length of the base of this triangle is just the x value, 15 times the cosine of 28, and the length here is just the y value, which is 15 times the sine of 28. So now I can focus on that other triangle, this triangle over here, and I'll see that the entire distance from the origin out to here is 20 units. And if I subtract the green part right here, I can get the distance from here to here, the rest of it, that red part. So that red part is basically 20, the entire thing, minus 15 times the cosine of 28. So let's focus on just this right triangle now. If you notice, this right triangle, I know one of the legs of it, I know the exact value. I know the other leg of it, the exact value. The only thing I don't know is the hypotenuse. But because it's a right triangle, I can use the Pythagorean theorem to find the hypotenuse. The Pythagorean theorem would say that this length squared plus this length squared is equal to a squared. So basically, 20 minus 15 square roots of 28 squared plus 15 times the sine of 28 squared has to equal a squared. That's just the Pythagorean theorem applied to this triangle here that's green. So once I have that, I can solve this for a squared by doing all the arithmetic on the right side, and I get that a squared is equal to 95.2314 approximately. Then to find a, all I have to do is take the square root of both sides. Square root of a squared is just a, while the square root of 95.2314 is 9.8. So there I found the length of this side right here. I found the value of a. So to generalize this, I'm going to look at this triangle here. It has all the information from the previous triangle, except instead of giving actual numbers, I've labeled the length of the base here C, the other adjacent side is B, and the opposite side is A, and of course angle A is just capital A. So I'm going to drop the altitude like I did before, and I'm going to look at this triangle on the left also, just like I did before. So for that triangle, I'm going to find the x and the y just like I did. And it turns out that y divided by b is the sine of angle A. So the sine of angle A is y over b, and x divided by b is the cosine of angle A. So the cosine of angle A is x over b, and that's this ordered pair right here, because the distance from the origin to here is the x value of that ordered pair, and the distance from the x-axis up to here, the point, is the y value. that tells me that this distance here is just b times the cosine of a, and this distance here is just b times the sine of a. The rest of the base of the bigger triangle, that red part, is just c, the entire length, minus b times the cosine of a. So I can focus now on this triangle on the right here. And I can use the Pythagorean theorem. By the Pythagorean theorem, I have that this length squared plus this length squared should equal this length squared. So a squared should equal c minus b cosine a squared plus b sine a squared. We can FOIL this binomial, giving me c times c is c squared, c times negative b cosine a is negative bc cosine a, and then I'm going to do that again for the inside, so I'm going to get another negative bc cosine a, so I have two of them, negative 2 bc cosine a. Then last times last is going to be b squared times the cosine squared of a. So I FOIL this, just bring this down and bring down the a squared. If I factor the b squared out of these two terms, I'll have b squared times the cosine squared of a plus the cosine squared of b. But the cosine squared of a plus the cosine squared of b is equal to 1 by the Pythagorean identity. So I get this. Rearranging this a little bit, this is the law of cosines right here. So the law of cosine says that a squared is equal to b squared plus c squared minus 2bc times the cosine of a. But that doesn't just work for angle A, it works for all of the angles A, B, and C, and these are the three formulas for the law of cosine. Let's go ahead and look at an example where we're going to employ one of these formulas. So here I have a right triangle, and we're being asked to solve for side C. So side C is just the base down here. We're being asked to solve for that length. To find side C, all I need is angle C and the two sides adjacent to angle C. So here's the formula. It says that c squared, the length I'm looking for, is equal to a squared, which is the square of 8, plus b squared, which is the square of 12, minus 2 times ab, which is 2 times 8 times 12, times the cosine of angle C. So that's the cosine of 118 degrees. 8 squared is 64, 12 squared is 144, and 2 times 8 times 12 is 192. Combining these like terms, 64 plus 144 gives me 208. Then I am going to just plug this left-hand side into my calculator to get that c squared is approximately 298.1385. And if I take the square root of both sides, I get that c is approximately 17.3. So that's how we use the law of cosines when we're given a triangle where we have an angle but we don't have the side across from it. Let's look at another example. In this last example, no angles are given at all. This is the side, side, side case. You're given 3 sides, no angles. The law of cosines can also be used in this case, the side, side, side case, and here it is. I have the 3 sides, C, A, and B. I just plug them in. I'm looking for angle C because they asked me to find angle C here. The 13 goes on the opposite side of the equal sign since I'm looking for angle C. That's really the main criteria here. I'm going to solve this equation now for angle C. First, I'm going to square all the numbers. 13 squared is 169, 10 squared is 100, 6 squared is 36, and 2 times 10 times 6 is 120. Then I'm just going to solve this for the cosine of C by combining these like terms first, and then subtracting the 136 from both sides, which leaves me 33 is equal to negative 120 times the cosine of C. Then I'm going to divide both sides by negative 120, and 33 over negative 120 is negative 11 over 40, so I get negative 11 over 40 is equal to the cosine of angle C. And if I want angle C, all I have to do is take the arc cosine of both sides. So I have the arc cosine of negative 11 over 40 is the arc cosine of the cosine of C, which is just C. Typing this into my calculator, I get that C, the angle I'm looking for here, is approximately equal to 106 degrees. And this is the application of the law of cosines.